In this video, we're going to be looking at the first isomorphism theorem for rings. And the first isomorphism theorem states the following. We're going to let phi be a ring homomorphism from R to S. And we're going to let I be the kernel of phi. And I want to remind you that the kernel is always an ideal inside the domain ring R. And so that means that the quotient structure R mod I exists. And the first isomorphism theorem says that that quotient ring R mod I just happens to be isomorphic to the image of phi. Now, to prove this particular thing, what we need to do is we have to find a ring isomorphism from the quotient ring R mod I to the image of phi. And that is a weird piece of notation. Let's clean up my notation. Now, a ring isomorphism, of course, is a ring homomorphism that is one-to-one and onto. And so I need to define some kind of a map. I'm going to start off by saying that I want to define a map, and I'm going to give it the name pi. And pi is going to go from the set of left cosets, R mod I, that quotient ring, to the image of R. And I want to be thinking about how I want to define this map. So I want to define the map in the following way. Well, I have to start with an arbitrary left coset from the quotient ring, and I need to feed it to the map pi. And since I'm going over to the target ring phi of R, well, the easiest thing that I can think of is maybe to make this guy nothing more than phi of R. Now, I kind of want to draw a map of what we're basically doing. The idea here is that we've got R going into S, given by phi, and every little r is sent to a phi of R that lives inside of S. And so what I'm basically doing is I'm simply saying, so let's now look at, for R mod I take R plus I, and I'm going to send him under this pi map to the same element, phi of R. Now, there are several questions, the first one of which is pi well defined? In other words, is pi actually a function? Now, the reason that's important is that it's quite possible for a particular left coset to have more than one name. In other words, if I know that R1 plus I is equal to R2 plus I, is pi of R1 plus I equal to pi of R2 plus I? And that's the very first thing that we have to be looking at very carefully. So, is pi well defined? So we're going to let R1 plus I be equal to R2 plus I, and this is inside the quotient ring R mod I. Now, I want to again remind you that we're looking at, is pi of R1 plus I equal to pi of R2 plus I? If the answer is yes, then pi is well defined. But if the answer is no, then we have problems. Now, in order to figure out the answer to this question, I have to go back to this basic hypothesis. So what I want to do is I want to note the following stuff. since we are assuming R1 plus I is equal to R2 plus I, we know that R1 minus R2 belongs to I, and I want to remind myself that I is the kernel of phi. And what that says, again, in lining up what we know, is that we know that phi of R1 minus R2 has to be the zero element in ring S, since phi takes R to S and I is equal to the kernel of phi. And so saying that R1 minus R2 is inside the kernel of phi says that phi sends the element R1 minus R2 to the zero element. Now, what I want to notice is this. Pi of R1 plus I, by the definition of pi, is just phi of R1. Pi of R2 plus I is equal to phi of R2. And what I want to look at is this. I'm going to think about phi of R1 minus phi of R2. Now, phi is a homomorphism, so that's going to be phi of R1 minus R2, and this is inside ring S. And it is because phi is a ring homomorphism. So we know that's what's going on here. But we also have already stated right up here that we know that phi of R1 minus R2 has to be equal to the zero element. So this mess is equal to the zero element inside ring S. And this is because R1 minus R2 is known to be an R, since R1 plus I and R2 plus I are exactly the same left coset. But now I've got an equation inside the ring S. So inside ring S, we have phi of R1 minus phi of R2 is equal to the zero element. But that's going to say that phi of R1 and phi of R2 are exactly the same element. But that's enough to say pi of R1 plus I is equal to pi of R2 plus I, and this is because of the definition of pi and how pi goes from the quotient ring to the ring S. I want to remind you that pi of any left coset is just phi of the coset's representative. And so what we do now have is that pi is indeed well defined. Now it turns out that's the hardest part of this particular proof, and we'll continue the proof inside the next video.